Wow, it's great to see you all here. Thank you all for coming. It's a very exciting meeting for me. This is really the introduction to the Photonics Center of our newest faculty member, David Boas. And David is a really exciting change of pace and a different direction for us. It's really diving into the field of neurophotonics, which is something the Photonics Center has been working on for a long time, and we're excited now to have a critical mass in that area. So I want to start by introducing David, and he will give a talk. Afterwards, I'm going to tell you a little bit about a neurophotonics community that we're trying to build here, and it'll just be about 5 minutes and try to recruit some of you graduate students into that community. All right, so David is the director of the Neurophotonics Center at Boston University. Its charter is sitting at the provost's office right now waiting for that last signature. So we will have a Neurophotonics Center, and the Neurophotonics Center will be affiliated in some ways with the Photonics Center, in some ways with the College of Engineering, some ways with the neuroscience. He's a professor of biomedical engineering. He received his BS in physics at Rensselaer Polytechnic Institute and a PhD in physics from the University of Pennsylvania. His research focuses on developing novel optical methods to study cerebral physiology and pathophysiology with a particular focus on studying brain function. So this is where neurophotonics comes in. He's developed methods spanning the length scales from microscopic capillary and cellular resolution to macroscopic measurements of human cerebral physiology through the intact scalp and skull. He's the founding president of the Society for Functional Near-Infrared Spectroscopy and the founding editor-in-chief of the Journal of Neurophotonics, published by SPIE. He's published more than 200 papers that have been broadly cited. In 2016, he was awarded the Britton Chance Award in Biomedical Optics for his development of novel high-impact biomedical optical technologies. There's an anecdote here. It says, he wishes it would snow more. So I'd like to welcome David to us and introduce him to you, and thank you all for coming.
Thank you, Tom, and it's really great to be able to come here and launch our new seminar series for neurophotonics as part of the NRT training program. Helen made me write down an anecdote, and it's not just, I think many of us want it to snow more. My son really wants it to snow more, and we've been building a snow machine. Now we just need it, which is easy to do actually, but you need it to be cold enough, and it's not cold enough, so it's really not cooperating. It was curious looking at Helen's announcement for this, and she gave me a title, which was to introduce you to neurophotonics. Of course, I was planning on giving a science talk, so I modified it, and I'm doing a bit of both. I'll start off with a few slides about neurophotonics, some history, some background. Then I'll say a little bit about the Neurophotonics Center that we are starting, and then I'll go into a science talk, which is also kind of historical for me. So neurophotonics, it was fun for me looking up this definition because like I imagine many of you, kind of wondered what's the difference between photonics and optics. Now I think I understand, right? So once I look at Wikipedia. So, as it says here, photonics is anything to do with the generation, detection, manipulation of photons. So that makes it pretty easy to define what neurophotonics is. It's just generally applying photonic methods to detect or manipulate neurons. Not just neurons, of course. There's many other important components of the brain. Glia and the vasculature are some nice examples. Optical methods or photonic methods applied in the neurosciences has always been the case. This term neurophotonics is relatively new. I think 5 years ago is probably when I first started to hear the term. I'd really like to kind of get down to the origin of it, though, to see where it first appeared. It was in 2013, SPIE came to me and asked me what I thought about a journal called Neurophotonics. And that sounded pretty exciting when I looked at the literature and just saw the growth of optical methods that were being developed for specifically applied to neuroscience, it seemed like this niche journal would really have a high impact in terms of bringing together the community of people. In our second volume, we recognized who is arguably the father of neurophotonics, Larry Cohen, and just taking some excerpts from the introduction of that. Larry Cohen, if you don't know, is really the pioneer of voltage-sensitive dye imaging. And he started off in the late 1960s using optical methods just to look at the optical changes from axons during action potential propagation. He's looking at light scattering and birefringence. As in the early 70s, he really started to survey thousands of different molecules, fluorescent and absorbing, to see which ones would be good indicators of the membrane voltages on axons. In 72, they hit upon the first successful molecule, this merocyanine 540, which enabled them to measure optically action potential propagation, and that really began the era of optical recording from many neurons simultaneously. So we recognized him in a special issue in the journal Neurophotonics as really the pioneer and father of neurophotonics. So emerging from there, Miriam Grimwald started working with Larry Cohen to map neuronal activity using voltage-sensitive dyes. So this was before we had fast CCD cameras. They were using photodiodes. They made arrays of photodiodes, and so it was very expensive, but you can get an array of 120 some photodiodes, and you could spatially map these voltage changes in the intact brain. So this time scale, here this bar is 200 and some milliseconds, and during a whisker stimulus in a rodent, they could get localized changes in membrane potential. Miriam Grimwald was a smart guy, is a smart guy, and he recognized that they were dealing with hemodynamic changes in blood volume, oxygenation of the hemoglobin, that was confounding their interpretation of these signals, because during neuronal activity, there's a blood flow response that changes the amount of hemoglobin, which changes the absorption of light, which was just confounding their interpretation of these fluorescent signals. So Amiram realized, well, instead of looking at these fast neural signals, we could just look at the intrinsic optical signals arising from changes in the hemoglobin concentration. And so looking at a slower time scale, because that hemodynamic response is always slower than the neural response. So you looked at that slower response, and now there's no fluorescence. This is just the change in reflected light being modulated by the amount of hemoglobin present in the brain. They could localize the brain activity very much the same way they could with the voltage-sensitive dye imaging. It's much easier because they didn't have to apply this exogenous dye to the brain. It had the additional benefit that it was slower, and so he could start to use cameras to get images of the hemodynamic changes reflecting the underlying neuronal activity. Right? So it's very difficult to image on a millisecond time scale in those days particularly, but you could image on a second time scale. And so Amiram Grimwald got famous for really developing the technology to allow him to image intensity changes from the brain that were being modulated by changes in the amount of hemoglobin that was modulated by neuronal activity. So he did a lot of studies with optical dominance columns, looking at just checkerboards kind of flickering and moving in different directions, and they could map out these ocular dominance columns. He did studies at different wavelengths, and it was interesting to see at 500 nanometers versus 800 nanometers, just the signal changes at 500 nanometers, 540 nanometers were larger just only because the absorption of hemoglobin in the green light is much stronger than the absorption in the red or near infrared. Right? So there's an order of magnitude more reflectance changes in green than in the red. And this is absorption spectrum of oxygenated hemoglobin versus deoxyhemoglobin is something I'll come back to later. Okay, so a story which I'll also briefly come back to is this dip. Amiram Grimwald really liked to talk about improving spatial resolution. This hemodynamic activity was kind of a distant relation to the underlying neuronal activity. And neuronal activity would give you a local dilation of the arterioles, which would give you a blood flow increase that happens over a larger area. He would call it watering the garden for the sake of a single flower. So he wanted to try to get a hemodynamic measure that would be more reflective of the more localized neuronal activity. So he talked about this dip, this early decrease in oxygenation of the blood that would be more reflective of where the neuronal activity was. It was a debate that lasted for 20-some years, and I'll come back to that. So to improve spatial resolution even further, really at the same time, 1990 was the advent of two-photon microscopy. And it's interesting, in the first paper in Science, they actually don't have a diagram of their two-photon microscope, but they had a patent issued in 1991, so you could look at the patent, get a drawing of their microscope, and in that same patent application, they showed the expected principle of two-photon microscopy, that the fluorescent signal would increase quadratically with the laser power. What I found interesting, and I'm sure there are people here who can tell me more interesting details of this story, they did not, or they were descanning the fluorescent signal. This is what you do with confocal microscopy. You have to, you raster scan the laser beam over the sample, and with confocal microscopy, you take the reflected or fluorescent signal, descan it, put it through a pinhole. That pinhole rejects all of the out-of-focus light, so you could really improve that depth sectioning. With two-photon microscopy, you don't have to do that. Yet, somehow in this original paper or patent application, they didn't realize that. Quickly later on, of course, they realized they didn't need to descan that for two-photon microscopy, and they put their detectors much closer to the objective to really enhance the amount of light that they could detect, so they could go deeper into the brain. It was very quick after that first invention of two-photon microscopy that was being applied to neuroscience applications. Already 6 years later, it was being used to image in vivo calcium dynamics in the rodent brain, and so they could. Today, of course, we have transgenic labeling. In the early days, they had to inject the calcium indicator into the cells, very painful. But then you could, with two-photon microscopy, get an image of the cell with a calcium indicator, and during action potentials, actually see changes in fluorescence that were indicative of the calcium concentration changes. Of course, then quickly after that, and something I'm very interested in, David Kleinfeld was using two-photon microscopy to image the vasculature. And so in this first demonstration, they were able to image the vasculature in vivo in the rodent brain down to 550 microns. So this is showing a cross-section in depth. This is an en face image. He could then go in and do line scans on individual capillaries, and you could see red blood cells passing through these capillaries. And he makes these really nice diagrams where the dark spots are the shadows of red blood cells passing through a capillary. And if you look at the slope of those shadows, this is a plot of time versus length along the capillary. That slope is really telling you what the speed of the red blood cell is. And so he was able to use this method to really look at changes in RBC speed during neuronal activity. And these are some of the first really microscopic measurements of that neurovascular coupling. How is the blood flow responding to neuronal activity in order to support the increased metabolic demands of that neuronal activity? And it's this neurovascular coupling which is really the basis of human functional neuroimaging. First with PET in the 80s, positron electron, PET, yeah. Whatever. I just want to talk about fMRI and optical methods. Functional magnetic resonance imaging came around in 1991. It was the 80s was a decade of rapid growth for MRI, and my colleagues at Mass General were doing a lot in this domain. And in 1991, they actually showed that they could map human brain activity by using a contrast agent to measure blood volume. And during a visual stimulus, they were actually able to see the occipital cortex activate changes in blood volume. And the very next year, they were able to demonstrate bold fMRI. So they didn't need a contrast agent. They could just use the endogenous contrast that are arising from the deoxyhemoglobin. Deoxyhemoglobin is paramagnetic. Oxyhemoglobin is diamagnetic, so that deoxyhemoglobin actually modulates the magnetic field, and they can measure that with MRI. And they didn't need an exogenous contrast agent. And so this really led to the advent of modern fMRI and has really revolutionized functional brain imaging in humans. The very next year, in 1993, functional near-infrared spectroscopy was demonstrated by my friend Arno Villinger and colleagues in Japan as well. And they just recognized, Arno actually came from Mass General, was working with Bruce Rosen, so he was well aware of this work, and he knew that hemoglobin was absorbed by light, and that red light, near-infrared light, absorbed hemoglobin weakly, and that he could get near-infrared light that propagate through the human scalp and skull. And so shortly after the fMRI demonstration, he showed that with near-infrared light, he could measure human brain activity the same as fMRI. And so using different colors of light, you can actually do the spectroscopy and map changes in oxygenated and deoxyhemoglobin. So you can get more at the physiology of that neurovascular coupling. Whereas fMRI, this bold signal, is really just reflecting deoxyhemoglobin. It's not even calibrated, so you don't even know what the concentration changes are. This is the figure from Arno Villinger's first paper, actually showing during that, this was a cognitive task. They were measuring the frontal cortex, prefrontal cortex. And during the cognitive task, they saw an increase in blood volume, increase in oxygenated hemoglobin, this delayed decrease in deoxyhemoglobin. Very typical hemodynamic response to neuronal activity. One other technique I'd like to tell you a little bit about, because it came out at the same time, 1991, is optical coherence tomography. This is now a $1 billion industry in ophthalmology. It's to date had little impact in the neurosciences, but it's really beginning to have impact in the neurosciences. And I think over the next decade, we're going to see a lot more impact. It's an area that I've been researching in and am pushing further. The OCT, basically the way it works, it puts pulses equivalent to pulses of laser light into the brain, measures the reflectance versus depth. So you get a depth profile like this. You raster scan it over your sample so you can get a volumetric image. If we look at an XZ image of the brain, there's not much to see in just the backscattered intensity, but if you look at the Doppler mode, so you can look at Doppler changes because of the moving red blood cells, you can get a color image of where the blood is flowing. And what's nice is if you then render this over a volume, you can get these exquisite angiograms, volumetric angiograms of the vasculature. And there are many things you can do now. Of course, you can go in and quantify blood flow in all of those individual vessels, quantify the flow changes during brain activation. We've demonstrated you can actually look at the dynamics of intracellular organelles, right? And so that's really reflecting cellular vitality. So I think there will be interesting applications there. And there's been a few demonstrations that you can actually measure neuronal activity intrinsically with OCT. So just measure the optical scattering changes and birefringence changes of the axons during action potential propagation. So I think there's potential there for OCT to have impact. So that was all really like 85 to 95, quite a lot of technology development. Of course, and really the foundation of neurophotonics. Since then, of course, there's been a lot more advances. I'm not going to detail it. You know, we'll have more seminars over the coming months and years on super resolution microscopy, fluorescent proteins has really had a dramatic impact in neurophotonics, optogenetics, of course, imaging freely behaving animals, and adaptive optics all are having profound impacts in neurophotonics, advancing rapidly, and representing just tremendous growth areas. So that brings us to BU and the Neurophotonics Center, which we are launching, and really just reflects the tremendous community that already exists in photonics and in neuroscience. There's already a lot of exciting neurophotonics work going on, and we just want to build a stronger community to enrich that and make it better for all of us. here at BU, but also more broadly in Boston and nationally and internationally. I really think there's an opportunity, particularly since this term, neurophotonics, is so new. We really, by latching onto this, have the opportunity to brand this and become a world-leading site for neurophotonic advances. Of course, our goal is just to understand how the brain works in health and disease, and there's just vast number of examples of how optical methods can be applied to help us understand how the brain works in development and in aging and decline, and broadly speaking. So the center is really going to support the development and early adoption of novel technologies to really advance our understanding of the brain. Will be interdisciplinary and interdepartmental, not just the School of Engineering, but broad across the neurosciences as well. And one thing I'm excited about is really focusing on these like maker and advanced user spaces. So not traditional core facilities, right? Because traditional core facilities are traditionally commercial instruments that work and are supported by commercial industry. Neurophotonics is really all about using cutting-edge technologies that don't really exist today, but they exist tomorrow. And so we want to implement those technologies in a facility that enables more people to get access to them at the very early stages. Of course, at the very early stages, the technology is changing every other week, and that can be annoying for some people. And so they want the technology to stabilize a little bit. And so that's when we'd move it into an advanced user sort of space where it's a little more stable. So you can imagine running a study for a few months. Once it becomes a bit more robustified and is not changing every few months, then it would become more a core facility. So the infrastructure, is still being planned, but the lab space will primarily be over in the Life Science Engineering building on the second floor. There will be a core space for functional neurospectroscopy in SILC next to the fMRI. There's going to be various optical instruments to be developed, and so we're brainstorming now what are the best technologies to develop and implement. And there will be animal handling and surgical operations, as well as labs for fabricating instruments, electronics, fiber optics. Thrust areas that we've identified so far, and this is actively evolving, so come talk to me if you have other ideas. One thrust area is optical imaging and neuromodulation in freely behaving animals. So we already put in a center grant to the NSF into the NeuroNext program. It's being reviewed this month, so fingers crossed, everyone. We'll see how it goes. So I think this will be a big thrust area for us, is really trying to miniaturize all these big microscopes so that we can do these studies in freely behaving animals and get access to a much greater repertoire of natural behaviors. Another area that is greatly needed in the neurosciences and also draws on a lot of technical strengths here at BU is just imaging deeper. And you can achieve that with 3-photon microscopy, adaptive optics, and controlling light scattering through tissue. So I think there's a lot of opportunities there. And keeping with this theme of freely behaving animals, we can do studies in freely behaving humans, a version of animals, with wearable functional near-infrared spectroscopy. And so if you have other ideas, please share them. Let's discuss. This is actively evolving. So now I will slide into my science talk, if that's okay, Helen. So I last gave a talk here a year ago. So I couldn't give the same talk. So I found more material. I've got a lot of material. So I was really excited to come back to this material. So it's a little old, but I think it couples very nicely with the introduction we just talked about. And you'll see, because it draws on all of those early methods I was talking about. And we were developing this intrinsic signal imaging, to better understand the neurovascular coupling. And ultimately, actually, I started working at Mass General shortly after the advent of fMRI, And the reason an MRI center hired an optical person actually was to help them better understand the origins of the fMRI signal. And so that really required developing optical methods to help us better understand neurovascular coupling. And in case you don't know, but people used to think that vascular response to neuronal activity was there in order to support the energetic demands of neuronal activity. So it was thought to be a feedback mechanism. It was responding to these increased energetic demands. Through our studies, though, we actually found that it's a feed-forward mechanism. And so I'll show you the studies that we did. So backing up a little bit, reiterating something I said, but saying in a little bit more detail. You present a stimulus to a subject, a sensory stimulus, produces a neural response through neurovascular coupling. It results in arterial dilation. Because that reduces vascular resistance, blood flow is increasing to that local region where there's increased neuronal activity, which actually washes in more oxygenated hemoglobin, washes out deoxyhemoglobin. Because deoxyhemoglobin concentration is modulated, it actually perturbs the fMRI signal, and you can get an image of that with BOLD. So we can use optical methods to really kind of interrogate and image the system at each one of these steps to better understand this neurovascular coupling, right? So we're using CCD-based intrinsic optical signal imaging, near-infrared spectroscopy, two-photon microscopy, and neuronal imaging as well with voltage-sensitive dyes. So the questions we're going to address about this neurovascular coupling is, what is the spatial relationship? What is the role of excitation and inhibition in the vascular response, in the metabolic response? Translate this to humans, and then bring it back to rodents to dig even deeper. So when I started out, it was shortly after Amiram Grunwald was getting all of his mileage with his cameras. That was all single wavelength. And he was trying to infer what the oxy and deoxyhemoglobin changes were. So I had the advantage of being 10 years later, and the cameras were a little better. So we were able to easily do multicolor imaging, which surprisingly nobody had done at that point. And by doing this multicolor imaging during 4-pulse stimulation was one of our favorite stimulus paradigms to give to the rodent. We could map out images of oxy and deoxyhemoglobin changes, right? So this is showing a localized oxygenated hemoglobin change during 4-pulse stimulus that we're able to image with this multispectral camera. You can do two-photon microscopy in the same prep and look at the individual arterioles now and see during the stimulus that arterial diameters are dilating, and we look at the veins and we actually see no venous dilation. This was actually important because in the early models of the fMRI BOLD signal, they talked about a venous balloon model. So they imagined that the veins were actually dilating during brain activation. And so we were doing all these studies looking for this venous dilation, and we couldn't find any, right? So that's caused a lot of people to rethink, this simple model of the fMRI BOLD signal. But we could delve much more deeply than that. So I was very fortunate to start working with Anna DeVore. She came to Mass General as a postdoc, actually to work with Anders Dale in the magnet. And I was incredibly fortunate. I think that was 2001. The magnet was broken. So she came to work with us using optical methods. And she was a very good neuroscientist, first neuroscientist I was able to work with. And so she just did an exhaustive series of studies using this multispectral imaging and very careful stimuli. So a single whisker deflection and looking at these localized changes in oxy and deoxyhemoglobin. And I was talking to you about the dip earlier. I think still today, this is the only example of a true vascular or hemodynamic dip in the brain activation signal. So this, I say a true dip because what Amiram Grunwald always talked about was that you'd have an early deoxygenation of the hemoglobin because of increases in oxygen consumption that you would observe prior to blood volume changes arising because of arterial dilation, right? But nobody ever actually showed changes in oxygenation occurring when there was no change in blood volume. I think still this is the first and only data set that shows this decrease in oxyhemoglobin and increase in deoxyhemoglobin with no changes in total hemoglobin concentration during the first second following a stimulus. The traditional hemodynamic response, of course, lasts for several seconds, and this is what people typically see, where you have this increase in oxyhemoglobin, this delayed decrease of deoxyhemoglobin being pushed out of the venous side. So these are just really nice images. What's interesting, and we'll come back to this, is if you look in the surrounding territory, this is the whisker barrel cortex, but surrounding it, we actually see some negativity in the signal. So here deoxyhemoglobin is decreasing, but surrounding, we're actually seeing increases in deoxyhemoglobin. So we'll come back to that. Why is that a negative activation signal? Is that a passive blood steal effect, or is there some active neural process that's causing that to happen? Okay, but let's first look at traditional neural responses and relate it to the hemodynamic response. Right? So Anna did a parametric study where she deflected the whisker many different amplitudes. In this first study, 9 different amplitudes. And so she could look at the hemodynamic response in response to deflections of 9 different amplitudes, and she measured traditional electrophysiological measures, multi-unit activity, local field potential, and could then look parametrically, how does the hemodynamic response grow with stimulus amplitude? How does the local field potential, multi-unit activity grow with stimulus amplitude? And the electrophysiological parameters were actually saturating, but the hemodynamic was continuing to grow. So is this suggesting a nonlinear coupling between neuronal activity and the vascular response? We hope not. I mean, life is much easier if it's a linear model. But this first data really looked like it was some nonlinear coupling. So she started to do some more studies and really found that it really looks like the hemodynamic, and this makes perfect sense, is spatially integrating the neural response. So it didn't make sense to measure the electrical response in a single barrel field when the hemodynamic response was really integrating the entire barrel field in the rodent. So she put electrodes into many different barrels and looked at the response to that single whisker deflection, and sure enough saw that the barrels at the principal barrel of the whisker that was being stimulated saturated, but as she went barrels that were further away, she saw more of this linear growth, right? So this is really suggesting to us that, and confirming that the hemodynamic response is growing because it's integrating the neural response from all of the barrel fields. Okay, but what about that surround negativity, right? So we actually thought that that was a passive stealing of blood from the surrounding cortex in order to deliver more blood to the activated brain region. We actually wrote a couple papers on that, which were fortunately rejected from like 3 different journals because we were wrong. I mean, the data was convincing to us, but it kept getting rejected. So we had to go back, do more measurements, and we found that actually it was an active neural process. So just looking in a little more detail at this hemodynamic response, in the center we drew these concentric circles around the center of activation. In the center you get a big increase in oxyhemoglobin, but as you go more and more to the surrounding territory, you could see a decrease in oxyhemoglobin. You had the same behavior for total hemoglobin and deoxyhemoglobin. So Anna went back and did just traditional voltage-sensitive dye imaging, and we could draw those same concentric circles. So when you see red, an increase in fluorescence, that's happening because of depolarization of the cells during neuronal activity, and the blue, a decrease in fluorescence, is actually the hyperpolarization of the neurons. And what she saw was in the center of activation, as you would expect, strong depolarization. Following the depolarization, there's some hyperpolarization of the cells. But more in the periphery, in the surrounding territory, there's very little depolarization and a lot more hyperpolarization. Right? So it's easy to see now, if we normalize the depolarization as we do here, you can see that surrounding territory has a lot more hyperpolarization. And so that hyperpolarization is coming from inhibitory signaling, and what it suggested was this really simple model of depolarization is driving vascular dilation. Hyperpolarization is driving a vascular constriction. Before going into that in more detail, of course, Anna was very good, ran a bunch of 2-photon microscopy experiments to really understand better what was going on, and she saw that in that center of activation, there was arterial dilation. In the surrounding territory, you could see some arterioles would try to dilate, but then they'd have overwhelming constriction. Right? So we were able to take these time courses and then fit it with a really simple model. You can have a vascular dilation model and a vascular constriction model, and we could fit all of those experimental responses with a superposition of those two models. Right? And you could get a ratio of the constriction ratio, constriction divided by the amount of dilation. And what we saw is that as we go further away from the center of the activation, there's relatively more constriction, which fits with this model of relative, or these measurements of relatively more hyperpolarization, right? So it really points towards this really simple model of neurovascular coupling where depolarization is releasing vascular active agents that cause dilation of the vessels, and hyperpolarization, the cells that are hyperpolarizing are releasing vasoconstrictive agents. So looking at that a little bit further, we wanted to try to trick the system, and so Anna came up with the clever idea of looking bilaterally. So if we stimulate a 4-pulse stimulus, you actually get bilateral activation. Traditionally we look at the contralateral hemisphere, where you can see your localized increases in blood flow, but you also get a response on the ipsilateral cortex. So now I'm bringing in laser speckle imaging. So we were doing, everything I showed you so far was multispectral imaging. We could look at hemoglobin, but we can also use laser speckle. And the speckles fluctuate because of the moving red blood cells, and by looking at the fluctuations of those speckles, we can measure blood flow. So let me just divert a little bit. So if you illuminate surface of the brain or any surface with incoherent light, you get a nice smooth image. If you use laser light, you actually get a speckle pattern, which is rising from the constructive and destructive interference of that coherent light reflecting back at you. If that surface is actually moving, you'll see that speckle pattern fluctuating, right? So we can either measure temporally those fluctuations, or we could measure a spatial speckle contrast. So it's really simple to measure a spatial speckle contrast. So this is actually laser light reflected off of the surface of the brain, and you can see a speckle pattern. You can actually see some vasculature here as well. But if we look at this local region of interest and look at the statistics of the speckle intensities, you get a very broad distribution, and so that has a high speckle contrast. The contrast is just defined as the standard deviation over the mean. If you look over this, what is apparently a vessel, you'll see the distribution is very narrow. And basically what's happening is the standard deviation is small because over the integration time of the camera, the speckles have fluctuated, and the contrast is smoothing out over the integration time of the camera. So if we just quantify this contrast, spatially, the same data becomes this. And that always astounds me, that this image comes from that data, right? All we're doing is looking at the spatial statistics of the speckle intensity. And you can get this amazingly exquisite pattern of the vasculature. And that contrast is related to blood flow, right? So the more blood flow, the less speckle contrast, right? So we use that with our multispectral imaging, and we can image not just changes in hemoglobin concentration, but we can image changes in blood flow, right? So we can do a 4-pulse stimulus, so looking at both somatosensory cortices on the contralateral and ipsilateral side. Here we see a localized decrease in speckle contrast. That's happening because there's an increase in blood flow during the 4-pulse activation. On the other hemisphere, interestingly, speckle contrast goes up, which is suggesting that blood flow is going down, right? So we can just plot ROI time courses. You see speckle contrast going down because of blood flow going up. On the contralateral cortex here, speckle contrast is going up or blood flow is going down, right, in the ipsilateral cortex. So the conventional wisdom at that point was that flow increases to support metabolic demand, right? It was this feedback mechanism. The reason we have this vascular response to brain activity is to support increased metabolic demand. So if we observe that flow is actually going down in the ipsilateral cortex, that would suggest that metabolism is going down. But that's strange. We know there's increased neuronal activity there. If there's increased neuronal activity in the ipsilateral cortex, there should be increased metabolic demand and flow should go up. So we were scratching our heads about this. So Anna went and did the voltage-sensitive dye imaging and saw the classic patterns in the contralateral cortex. We get a strong depolarization followed by some hyperpolarization. When we looked in the ipsilateral cortex, there was not as much depolarization, but there's relatively more hyperpolarization, right? So it comes back to that same story. It looks like the depolarization is driving a vasodilation, and the hyperpolarization is driving a vasoconstriction. And we just kind of teased the system. We fooled it. We fooled it so that on the ipsilateral cortex, the hyperpolarization actually beat the depolarization, and we fooled it into decreasing blood flow. Even though in this transient state there is increased neuronal activity and there should be increased metabolism, we kind of fooled the system into decreasing blood flow, right? And this all kind of makes sense from an evolutionary perspective, right? So that inhibitory signaling, is setting up the brain to actually reduce neuronal activity, not immediately, on the sub-second time scale, but over the seconds or minutes sort of time scale, right? So we won't actually see a decrease in neuronal activity for tens of seconds if this stimulus was sustained. So the system with the blood flow response is anticipating that neuronal activity is going to decrease, and so it doesn't have to increase blood flow, right? So that's really suggesting to us that it's really very much a feed-forward system anticipating that neuronal activity would ultimately go down. Of course, we fooled the system here by just doing a single whisker, a very brief stimulus, 4-pulse stimulus actually, in this case, very brief. And so the system never actually reduced neuronal activity, but it was anticipating a reduction in neuronal activity. Okay. These were 2 photon measurements showing the same thing of a vasoconstriction. So it really, all of these data would suggest, if we believe the blood flow data, that metabolism went down. But of course, with all the neuronal activity going on, metabolism would go up. So we had to measure metabolism. So we were very lucky to work with Christian Weber, who is an expert in 2DG autoradiography, which allowed us to quantify glucose uptake during this stimulus. And so in the contralateral cortex, we saw the traditional increase in glucose uptake, indicating increased glucose metabolism. And we had to analyze hard to see what was happening on the ipsilateral cortex. But when averaged across all our animals, we saw that statistically significant increase in glucose metabolism. Okay, so just conclusions of this section, we found that the functional excitation is correlated predominantly with active dilation of the arterioles, but this inhibition is really sending a vasoconstrictive signaling to the vessels. And the hemodynamic response is governed by a feed-forward signaling, not by feedback to meet metabolic demand. So this was really going against the conventional wisdom at the time. So now we want to bridge this to humans, right? So we made these observations in animal models. Can we observe this in humans? And so Mariangela Franceschini, working with near-infrared spectroscopy combined with magnetoencephalography, wanted to perform the exact same sort of experiments in humans, right? And look at components of the neuronal response as measured by MEG and relate it to the hemodynamic response, right? So functional near-infrared spectroscopy is very much like intrinsic optical signal imaging, but we're doing it in humans, not the exposed brains of rodents. And basically, it's just that the hemodynamic changes are reflecting the underlying neuronal activity, It produces changes in hemoglobin concentrations, which changes the amount of light absorption. Optically, we measure those changes in the light being reflected back to the surface of the scalp, and we can quantify the changes in absorption and relate it back to then the hemoglobin concentration changes if we make measurements at 2 or more wavelengths. Light in the near-infrared region is able to scatter through the human scalp and skull to interrogate what's happening in the brain, and this is showing a sensitivity profile. We are sensitive to the absorption changes that are occurring in the cortex, close to the skull. Okay, so we can map out, those hemodynamic changes that are evoked by brain activation. This is 5 subjects, and these are the red dots are showing the optoid locations for the NIRS measurements. Underlying it is the MEG image during a median nerve stimulation. And then in contours, I actually show the optical images of the hemodynamic changes that you can actually see are co-located with the electrical changes that were measured with MEG. So looking at the hemodynamic changes, there was a parametric median nerve stimulation. So that's a 3 hertz stimulus that was presented either for 1 second, 2 seconds duration, 3 seconds, or 4 seconds. This is averaged over 6 seconds. This is the decrease in deoxyhemoglobin. And following, at the time, what was being done with fMRI, we wanted to take the 1 second response to predict the response at longer durations. And we found we couldn't predict it, right? So this was really suggesting that there was some sort of nonlinear relationship between the response at 1 second and the response for longer duration stimuli. It was interesting, if you take the 2 second response, you could actually perfectly predict the response for a 4 second duration stimulus, right? So it was really suggesting some nonlinearity was going. And at the same time, people were recognizing this with fMRI. And so the question was really, is this nonlinearity happening because neurovascular coupling is nonlinear? Or is there some nonlinearity in the neural response, right? And then there's linear coupling between neural and vascular responses, right? So we needed to tease that apart. So what Mariangela did was then break up, this is the time course of the MEG response, and you can identify the individual components. So you can identify this negative response at 20 milliseconds, which is arising mostly from postsynaptic currents from the pyramidal neurons. There's the positive 35 millisecond response from the inhibitory postsynaptic potentials. And then there's later latency responses as well that are coming from a larger area and a larger neural population. So you could really kind of take the area under the curve for each of those components and set up a simple linear regression model to use these neural responses to predict the hemodynamic response. And doing that, you could take the N20, you can't really predict the hemodynamic response well. The P35 looks a little better, but still not perfect. P60, again, not perfect, but if you take the entire neural response, you can actually predict the hemodynamic response quite well, right? So it was only by including the longer latency neural responses that we were able to fully predict the hemodynamic response, right? So it's not just the neural inputs at the earliest times, right, that are driving the hemodynamic response, but it's the collective population, it's the full population of the neural response, right? Which actually makes it much more interesting that what the hemodynamic response is measuring with fMRI and FNIRS is that cortical activity. It's not just the sensory inputs into the brain. So that was very nice to kind of confirm that in humans, but there's only so much you can do in humans. So we went back to rodents using near-infrared spectroscopy to really tease apart more what the different components of the neural response, how they are driving the hemodynamic response. And so just doing a 4-pulse stimulation and measuring somatosensory evoked potentials at the same time as the hemodynamic response. So during the 4-pulse stimulation, you get thalamic inputs into layer 4, which then propagate up to the superficial layers. And so it's very easy to tease this apart in rodents from the somatosensory evoked potentials, where you have a P1, which is representing the thalamic inputs, as the N1 and P2 is more the cortical processing. And during a parametric stimulus, so she just varied the duration of a 4 hertz 4 pulse stimulation, and you can see actually the SEP, not much is changing. Maybe some habituation happening for the longest duration stimulus. As the stimulus gets longer, the amplitude of the hemodynamic response grows. Amplitude, not much interesting. You know, the SEPs pretty much always the same. As the amplitude, though, of the electrical stimulus gets larger, we see the SEP amplitude also gets larger and the hemodynamic response gets larger. Frequency is much more interesting because there's much more habituation going on. At higher frequencies, that neural response is greatly suppressed. So this is where we're going to have the power to be able to now distinguish which components of the neural response are driving the hemodynamic response. So setting up a linear regression model again, we can take the area under the curves of each one of these electrical components and put that into a linear regression model to predict the hemodynamic response. You see for a duration, all components predict the hemodynamic response equally well. For amplitude, you can see that P1 actually doesn't do a good job of predicting the hemodynamic response. The N1 and P2 do a better job, and that's really amplified well for changing frequency of the stimulus. The thalamic inputs into layer 4 are not driving the hemodynamic response. It's all of the later subsequent cortical processing that's driving the hemodynamic response. Okay. Right. So as a final result, you know, those data were obtained with a rodent under anesthesia and alpha chlorelose. And so there's debate in the literature at the time, and still is. You know, your animals under anesthesia, so the vascular responses you're measuring are not really representative of the brain activation you're measuring in humans, right? So how do you know neurovascular coupling isn't different if you're awake? And so in animal studies now, all measurements are being done pretty much in awake animals, so you get away from this anesthesia problem. But we wanted to just address the question, does neurovascular coupling actually change under anesthesia? And Maria Angela was very lucky. She had a medical student come to her who wanted to do a study, and the student was incredibly diligent and ran like 60 rodents, 10 in a group, 10 in each group with a different anesthetic to really get at this question, does the anesthesia change the neurovascular coupling? So in this case, just change the duration of the stimulus, a very similar parametric stimulation. This is looking at the train of somatosensory evoked responses under the different anesthetics. You can see that neural responses are strongly affected by the anesthetic being used, right? So makes sense. The anesthetics are acting on the neurons, so their ability to respond to stimuli is being altered in different ways by different anesthetics, right? So that's just showing you a close-up. The components are quite different, right? The hemodynamic response under different anesthetics is also quite different. Makes sense. Neural response is different. Hemodynamic should be different. But is that neurovascular coupling the same, or is it different, right? So we can start to set up a regression model, right? So you could just plot the somatosensory evoked potential amplitude versus the hemodynamic response amplitude, and you can see actually, you know, P1, everything's all over the map, but P2 and N1 versus the hemodynamic, you know, we got a good linear relationship except for one anesthetic, right? This ketamine xylazine is this outlier. But this is the only anesthetic in our group that was not a GABAergic anesthetic, but the ketamine xylazine actually works on the NMDA receptor, so it actually has a very different impact on the neural response. And in fact, it was the only anesthetic in which we saw this pronounced N2 response in the somatosensory evoked potential. So this made it really interesting for setting up a linear regression model, right? So as we set up the linear regression model, excluding the ketamine xylazine, you know, we found that the P2 regressor could accurately predict the hemodynamic response. And when we brought in the ketamine xylazine, you know, actually no single regressor could actually accurately predict the hemodynamic response. We had to bring in this N2, right? So it was this combination of P2 with N2 that accurately predicted the hemodynamic response. And what was really interesting is in that linear regression model, P2 was driving a vasodilatory signal, and the N2 was actually driving a vasoconstrictive signaling, right? So we actually saw this, repeated what we saw with the two-photon microscopy. Now we've repeated it with near-infrared spectroscopy and somatosensory evoked potentials. We needed this kind of competition between dilation and constriction in order, and related to, the underlying neural signals in order to predict the hemodynamic response. Okay, so the studies like this have really allowed us to disentangle the role of the different neural components and how it relates to the hemodynamic response. It's really that later cortical processing that's driving that hemodynamic response, which is really good for fMRI studies, right? Because if it was just the inputs, your brain, your cortex could actually be dead. The inputs are getting there, and fMRI would be measuring brain activity, right? But what you really care about is the local processing that's going on. And that really, our studies really support that that's what fMRI is really reflecting, is that local processing. So the negative somatosensory evoked potentials, at least in this model, really seems to relate to vasoconstrictive signaling. These data show that the neurovascular coupling is really unaffected by anesthetic. And we would predict, but we haven't done the study yet, that this neurovascular coupling would actually be exactly the same in a wake animal, right? So the difference between awake and anesthetics is the neural response, right? Absolutely, the neural response is affected by your anesthetic state or your wakefulness, right? But that neurovascular coupling is not really altered by the anesthetic. Okay, with that, I'll just summarize by telling you, I told you about the launch of the Neurophotonics Center, and I just told you about some of the work we did many years ago on using early neurophotonic methods to really explore this neurovascular coupling, to reveal that it's a feed-forward mechanism that's driving the vascular response to neuron activity, and the fMRI bold signal is really reflecting more the cortical processing and not just the neural inputs into the cortex. So I'd be happy to discuss this further, any and all aspects. So, thanks. Yeah.
So you usually look at hemodynamics. How does NIRS
Yeah.
compare to photoacoustic?
Yeah. So the FNIRS is putting light in. The light is being absorbed by hemoglobin, which is modulating how much light comes back out to the surface of the head for detection. Whereas photoacoustic tomography is putting a pulse of light in, a higher energy, and a pulse, whereas FNIRS is using continuous wave light. That pulse of light is absorbed by the hemoglobin, which produces some local heating, which produces a local sound wave, which you can then measure photoacoustically. Right? So the photoacoustics has this advantage that light only goes in and sound comes out, so it potentially has better spatial resolution. And it has not been demonstrated for human functional brain imaging, but it has been demonstrated for functional brain imaging in rodents, but it's not really done routinely, so the instrumentation is still evolving. I think it's a really exciting technology to watch, but it's way behind FNIRS in terms of the human translation, right? So the FNIRS has been applied in humans for over 20 years, and I think last year there was over 400 papers published. It's really mature to the point now that people are now engineering these truly wearable, portable systems that I think are going to have a profound impact on the types of brain activation studies you can do in humans as they're engaged in natural activities around campus, right? Right. Yeah, John.
So you've got this wonderful little linear black box between neural signals and some indirect neural signals and the vascular response. What's the effector? What's going on? What are the components of that black box?
Right. Well, so I've reduced it to, tried to reduce it to neural components, but of course, I've just said excitatory and inhibitory, right? So it's incredibly complex, the cellular underpinnings of excitatory signaling and inhibitory signaling, right? So I think.
I mean, sort of downstream from that. So you still have to have a couple through vessels.
Right. No. I think I'm getting at that. So what are the vasoactive agents that are being released from the different cell types that are then acting on the smooth muscle cells of arterioles to either cause the dilation or constriction? There are experts studying that. I'm not as versed on it as I should be in terms of those molecular pathways. Yeah. But I will say, and what I know a little bit more about, because Anna DeVore is working on it, is there's an incredible rich opportunity now using just optogenetic methods to stimulate specific cell types and see what the action is on the vessels, right? To really further confirm, the inhibitory activity versus excitatory activity and what impact it's having on the cell. So that's being done now, right? But the actual molecular pathways, people know that. I don't know it, right? Yeah.
So if you think about, I guess it's more about your view on the field of neurophotonics.
Yeah.
So if you think about the complexity of understanding brains, you listed a lot of interesting technologies there. I guess the difficulty is the problem underneath is multi-skills. So I wanted, what's your views on in setting up such a center, how to bring these multi-skill problems and how these different technology will interact?
Yeah, no, so what I love about just neuroscience, right? There's tons of problems that you can't address because you don't have the technology, right? So neuroscientists, I found, are just incredibly clever at adopting new technologies, right? So it's a perfect match for engineers and physicists who are really good at developing technologies to match up with neuroscientists who are really good at adopting these incredibly complex technologies, right? As opposed to, say, a clinician who has no idea, how to use a new technology. I hope there's no clinicians in the room. So that makes it really easy, right, to do this early adoption and early translation. And I think the people developing technologies are really hungry to apply it. They don't really know what the problems are, and the neuroscientists have tons of problems, right? They just need to be matched with the people making the new technologies. And in this room, we have a lot of both. And so I think it's going to just be really easy to solve a lot of outstanding problems just by matching some of the people in the room, right? So I think, what Helen, Tom, and I are hoping to do with the seminar series and more events like this is to facilitate the matchmaking, right? Does that answer? Yeah, all right.
Quick question here.
Yeah.
I wonder whether you can comment on the potential set effect of hemoglobin being heated up by the light.
Yeah.
Do they deteriorate, and what time scale this would become a problem?
Right, with regards to the photoacoustics.
Or just in general?
Yeah,
infrared
I mean,
light?
so our for near infrared spectroscopy or intrinsic signal imaging, the temperature rise is less than 1 degree centigrade, right? So, I mean, actually, I don't know how many people here are doing cranial window studies, but when you make a cranial window, the surface of your brain drops 5 degrees C, right? So something you might want to think about is whether or not you need to heat up that cranial window, because temperature does very much change the physiology, right? And so it's something to think about, right? So at least, so given that, I've never really been concerned about temperature rises of hemoglobin because of the laser illumination, because it's less than a degree C. Now, of course, we could raise the power, and this is a form of phototherapy. You could raise the power high enough that you coagulate the red blood cells, right? So that can be done. But traditionally, for these types of sensing applications, the temperature rise is negligible, right? Yeah, hi.
Very good talk. And you have mentioned in your slide that you have done the 5 groups from different centers. And I'm wondering about, did you have ever checked the difference between male and the female in terms of the dynamic response between male and female, also the difference between the different development stages?
I have not done that. People have certainly looked at the different developmental stages, and they're
So what's the result?
they're very interesting results there, right? So the results really suggest that in a newborn human and rodent, the studies have been both done in humans and rodents, the vasculature is not fully developed, right? So this neurovascular coupling, maybe the mechanisms are there, right? But the vasculature is not fully developed, so it can't respond in the same way. And that's been documented in the literature where those vascular responses are very different in newborn rodents and humans, right? Than they are in mature. So that maturity, in rodents, I think it's already mature by day 20. Don't quote me, I can point you to the paper. In humans, it's after about 3 months, roughly, that the vasculature seems to be fully mature in terms of producing a classic hemodynamic response to brain activation.
And also, have you ever checked the difference between the patient and the normal person, such as diabetes and other kind of cancer patients?
Yeah. So,
if so, that will be very exciting.
I have not. People have. I haven't read the literature exhaustively on that. I would expect there to be differences. I don't think people have robustly quantified it. So the reason I would expect differences is, again, like in diabetes, it has a profound effect on the vasculature, right? So the vasculature, certainly in extended diabetes, is not normal. And so you can imagine that the vascular responses would be altered. But I don't think that's actually been carefully observed.
Just to check, see, and see what happens.
Yeah. Alzheimer's disease models, I think people have shown different vascular responses, but then it depends on which model you're using. There's some models that have vascular effects and other models that don't have vascular effects, right?
And you have mentioned the genetics area, and maybe there have some link between epigenetics and the,
Yeah, sure, absolutely. Great, yeah.
Question is, have you thought about the section next steps in this research, looking into the further deeper into the hemodynamic response for example, cognitive functions or emotional response based on photo?
Right. So the extending this line of work, questions that need a little bit more development would be, where does the vascular response initiate? Because the optical methods have really only allowed us to go down, say, 500 microns. But we believe that the responses are initiating deeper. And so we need microscopy methods that allow us to go deeper to really nail that down. I already said about the optogenetic studies in terms of really getting at the inhibitory and excitatory signaling, the different cell types that are producing the vascular responses. So those studies are going on now. In terms of, I think part of your question was also relating to just human studies. Right. And with fMRI, it's 20-some years of just spatial mapping. It hasn't really done much in terms of quantitative physiology and what you can learn from that, because the bold signal is not really a quantitative signal. So I think progress is needed there. NIRS, or functional near-infrared spectroscopy, has an advantage. We can be more quantitative with the physiology, but our spatial resolution, our depth penetration is not as good. But nonetheless, I think there's many applications where FNIRS is good enough. And it has the advantage of also being a quantitative physiological measure. And I didn't show you today, but actually with the FNIRS extensions to laser Doppler methods, you can also get at oxygen consumption changes during brain activation, right? So there's these additional components of brain activity that you can measure in humans. And doing it in a wearable system, it's a field to get involved in, right? Because it's really 400 papers published last year. It's been growing exponentially for the last 20 years. It's going to continue that growth, for the next 10 years for sure.
Huge potential.
Right. Yeah.
So I'm just curious about sort of the combination of imaging modalities, because I'm wondering, like you said, when is it good enough that one modality alone can sort of give what you need, when
Yeah.
you have to sort of bring modalities in because they complement each other's
Yeah.
pros and cons. Because I'm starting to notice that I think there's potentially a trend towards combining imaging modalities for the fact that penetration depth could
Yeah.
be one thing.
Yeah, sure. So you just have to be really careful. So we spent the decade of 2000 to 2010 trying to do multimodal human imaging with, actually my colleagues are doing MEG and MRI. That's easy because those are two separate experiments. But like you want to do MRI and EEG, or MRI and FNIRS, or FNIRS with MEG, you've just like doubled or tripled or made it worse, the possibility of the experiment failing, right? And so I think after 10 years of trying, we don't want to do any multimodal human imaging anymore. So it's really difficult. Now animals are much more easy to train than humans, or they're much more resilient. So I think there's a lot of interesting things to do in terms of multimodal studies, particularly in the animal models. And so then really the caution is just choose your modalities carefully, right? So that you're not reducing the probability of a successful experiment to zero, right? Yeah, but there's certainly a lot more to do there. And I mean, you'll see that with the technology development, is the challenges of combining those technologies, right? So there will be a lot more to do there.
All right.
Yep.
Let's thank
Yeah.
David one more time.
My computer's a little slow. I'll find it. Tom has a few things to say, so don't go anywhere.
Oh, yeah, you can't go yet. 6 slides, though. That's it. 6 slides, maybe 7. Oh. It just takes a minute. It's because of that slow computer. Yeah. Okay, so I'm going to tell you in 4 minutes about the Neurophotonics training grant. So we have an NRT, that's an NSF research training grant. And this grant just started this year, and I want to tell you a little about it and what it means to you. First of all, if you're a graduate student sitting here, and you're doing work that you think is pretty closely related to neurophotonics, that is, you use light and you think about neurons, raise your hand. Okay? High. Raise your hand high. Thank you. Oh, perfect. Okay, so this is most relevant to you. How does this go forward? Spacebar, of course. That would be arrow. The arrow, and then the spacebar. Okay, so the NRT is a federally funded program at BU. It's about a $3 million program altogether to support a cohesive and inclusive community of graduate students with common interests in neurophotonics. There's a special part of that program that involves recruitment of broader, diverse set of students from different backgrounds. But the program is open to everybody. So that program will use anybody who's using light-based tools to understand the brain can be part of it. There's faculty associated with it. In addition to me, there are these 12 faculty. About half or maybe 3/4 of them are in the room right now. These faculty members are, why is Jerome Mertz pointing at everybody? I don't understand that myself. And so these faculty are the core faculty, but they're not. It's not exclusive. If you're working in neurophotonics and your advisor is not on this list, you can still be part of this neurophotonics community. So what's it all about? We are trying to, right now we have to get students to join this center. There's no admission fee. You don't have to pay anything. We won't telemarket you. Our job is to try to start building this community. Because the program is starting now, we want to get some second year and further graduate students to be our inaugural members. And then we're going to start appointing people to soliciting memberships from students who are just joining BU. So entering graduate students, there's a whole series of labels we've put on you. Candidates, prospects, trainees. Don't worry about all of that. Right now, you're welcome to join. And then as we go on, we'll teach you about all the different levels of participation that we have. So any doctoral students who are conducting neurophotonics research can be part of this community. What happens when you're part of the community? Well, you'll get travel awards to conferences. That's the dangling carrot. That's kind of an interesting thing. So if you have a paper accepted and you present in an area of neurophotonics, then the NRT training grant can support your travel. Usually be some matching with your advisor. We're going to have training in communications, neuroethics, professional development, and we'll also have technical training. So we'll have sort of training in specific areas of neurophotonics. What you got today is a little bit of some of that. We could have different kinds of topics that we'll study. We're going to have seminar series like the one today. We're going to have journal clubs. So not everybody will get together in every journal club. There may be several journal clubs on different themes. There's one currently that meets every Friday on microscopy techniques. There'll be others around, and the Neurophotonics Research Training Grant won't be just one journal club, but several, and we'll support pizza at the journal clubs, right? So this is the kind of thing we'll do. And we're going to have an annual symposium. So next year's Photonics Center annual symposium is going to be on neurophotonics. Can you imagine who the host might be for that symposium? Yeah, right. Okay? And so if you're interested, you've got to confirm your interest at the check-in table. Watch for a link to the application. Where is the link to the application, Helen?
It's going to be delivered via email.
It's going to be delivered via email. Helen Fawcett, raise your hand, is the program coordinator for the NRT. So it's good and bad to know Helen. Once you know Helen and you're on her email list, you're on her email list. There is no unsubscribe to Helen. So that's it. But the good news is she will watch after you for all of your career here. So this is my encouragement to you, is join this group. That's the end of my evangelism. I thank you all for coming, and I want to thank David one more time for giving us a terrific seminar. Any questions? Happy to answer them. All right. Thanks.